has only one. Right? This is going to be there. But
I think that every term is positive here.
sorry?
In this series, every term is positive.
Okay.
Zero.
Okay. So you can also say that they are directly zero.
All of them.
Yeah. This is a good point. That since all these are positive, non-negative terms, and their sum is zero, so we have no other possibility except saying that zero. Now these are transition probabilities. Okay, you are transitioning from the state I to the state G. So what is the definition of a state leading to another state actually? That you get a positive probability. Okay, so what is the meaning of I leads to G? Definition. Probability that in n steps you can reach from I to G is positive. So this guy must be positive. So you have no other choice except saying that f star Gi must be 1. Okay? So this must be 1, and G is in a state that leads to the I actually. So can I say this? How can I say that G can be J as well? G can be J as well. Okay, so here's the thing. So I won't use this assumption. I leads to J. Okay, so one of the assumption is that I leads to J. What does this mean? Okay. Pij in n step is positive, and if it is positive, at least for this J, you're gonna say that f star Ji is 1 for sure. F star Ji is 1. You can also show by repeating the same process that f star ij is also 1. Okay? And what does this show? The f star ji is 1. What immediate conclusion you can have from f star ji is 1? That you can reach from the star j to the I. Okay? You can, so there is a positive probability, okay, that you can reach from the state j to I. That's what essentially shows that j leads to I actually. Okay? You can. Okay, so the theorem demands another thing, Fij. Okay, but you can.
Sir, because I leads to J, it's obvious.
I'm sorry.
I leads to J, we have assumed. So if Ij star must be for 1.
Yes.
It's obvious.
Okay, if I leads to J, can I say f star J must be 1? Have I seen any result actually or something like that? So there is.
We proved if that J is equal to 1.
So, जब हम
J is equal to 1.
Okay. You need to make the point rigorous actually. Okay, this is a claim actually that I leads to J means f star J, f star I J equal to 1. It seems intuitively yes, okay, but who knows? Who knows? So what does what does another suggestion that is coming is that you do the same analysis, but instead of starting for I, start from the J actually. And do the
Sir, then you would need f star jj should be 1 because we are using here f star I is 1.
Yes.
So we are using this assumption. If we are going the same way for j, we will need f jj to be 1 also.
F star jj to be 1, but doesn't this allow you to get that?
No sir, because I is recurrent here. We don't know j is recurrent or not.
सर
What do you think about the argument for this?
ये जो हमने पूरी कंप्यूटेशन की है वहाँ तक 0 के बाद वो जो आपने आर्गुमेंट यूज किया है बाद में I leads to J therefore तो ये सारी कंप्यूटेशन कहाँ पे यूज ये जो सारे
this Hari computation allows you that this product goes to 0 actually. This is, and it allows you to say that, you know,
Pij is positive.
Pij is positive. So we are for sure that at least that for this expression for j, maybe both are positive for the rest, but for Pij I know for sure that, you know, for g equal to being j, I know for sure that this is positive. So I have no other choice except j. Okay. In the rest of the cases I have no idea. Alright. You see, you know, you have such boring proofs. I'm not going to do any proof now. You have to, you know, do that for yourself. The things that you have to do. So let's read them out. Okay, so the final result that I would like to do in this sequence, and you see that all these things that you are doing are of very practical importance actually, especially when you can do agent angle calculus. Okay, so the next conclusion is another interesting conclusion, just mentioning it and then doing one example. Okay. So here is the theorem. So it says that if I have a class in a chain, okay, that is finite, okay, so you know the two things. So it gives a very interesting kind of a, you know, a sufficient condition to know that whether your states are recurrent or not. So if you have a class in the Markov chain that is finite, and you know this class or in each of the state in this class is essential. Okay, is essential. Then it is recurrent. Simple as that. This is very interesting result actually. And usually, for example, the examples are maybe what Google is doing it, they are dealing with the finite state chain set. So in a finite state chain, if you have a class, the only thing that you know about that class is that it's essential. You know that entire class is recurrent as well. Okay, that's what it says. So here's one example that illustrates some of the things that I said. So imagine I have a chain that contains 3 states, 1, 2, 3. So this result is valid. And the assumption this also is 1/3 and 1/3. And say 1/3. Locality and 1/3.
Sir, can we say this theorem is the converse of the last?
I'm sorry, can we?
Converse of the last theorem. Is this theorem the converse of the last?
If this theorem is converse of last, so what was the last theorem telling us?
That if I is recurrent, this
So if you have
recurrent
if you
state.
have a recurrent class, it's essential. Yes. You have a recurrent class, and it leads to some other class J. That state is it is intercommunicating, okay, and it's essential as well.
Yeah, it's the same.
So maybe the converse is not true in general, but for the finite.
Finally, yes.
So you have this. 1, 2, 3 properties. What can you say about the state 1? Is it essential, inessential? It's not essential because it refers to 2, but 2 is not referring back to 2. How about 2?
2 is referring to 3 and 3 is referring to 2.
Is essential and 3 is also essential. Can you guess which classes are going to be recurrent? But okay, if you know that that's a class and 2 and 3 both are essential, so they both are, what do you call it, recurrent as well actually. Okay, they both are recurrent, and one is transient actually. So that's what we mean by the transient. That once you leave, the state, you have no chances that you're going to return back. Actually, they are very minute chances. Okay. So what would be the transition matrix for this? 1, 2, 3. For example, so it's 1/3, 1/3. 0. I'm just writing it 0, 0, 1, and 0, 1, 0. Okay. So I can see that 1 is a transient class. It's not recurrent. But the question is, can I see it mathematically? So for that, I need to compute f star 1, 1. Okay. So the f star 1, 1 can be computed as, how can I compute it? So it's the probability that you are in state 1 and you return back to the state 1 plus the probability that you were in state 1, okay, state 1 in the beginning, and in the next step you are not in state 1, and then in the second step you are back to the 1, okay, and so on and so forth. So I know this guy is 1/3. So this is 1/3. That's what it tells you. So what is this probability? 0. Should be 0. Because what is the probability? You are at 1. Then at time you are, for example, not at 1, so you are in 2 and 3. But at time 2, you suddenly return to the state 2. So this is not going to happen. So this must be 0. So all of the other probabilities are 0. So you get 1/3, and hence this is less than 1. So this shows that this state is a kind of transient state. Can I talk about, say this guy, P, I, and this series, 0, infinity, 1 to infinity, this series. So what would be Pii, so it starts from 0. What would be the Pii 0? So I am at 1. So what is the probability that I am at 1?
1 by 3.
So you are sure that you are at 1. What will be the probability? P1, 1. So P 1 to 1, but in the one step actually. It's 1/3 about P1, 1, but in 2 steps.
1 by 9.
So I'm here and I'm returning back to it. So it can be 1/3 square and so on and so forth. So I can see that it becomes a geometric series and it converges. It converges. And you can also see that you can, to whatever this converges, that thing also satisfies this 1 minus f star 1, 1 relation as well. I know what is f star 1, 1. I know. So this is going to converge to what? This series is, what's going to happen with this series? So it's going to converge. I can compute the limit of it. It's not a difficult thing.
So we 1 upon 1 minus.
1 over 1 minus
1 upon 3.
1 upon 3. Anyway, so this is just one simple example that you can have similar kind of. ठीक है जी So what we did so far, classifying states without probabilities and then with probabilities, and what is their interconnection. Now I would like to address the key theorem, the key question that we have been asking since quite long, is that in long run, what will happen with such a result? So think about it. So I have a chain in which people are there is switching of state is being going on. Okay. So this is happening. So keeping in view these results or some of these results, what is your intuitive prediction actually that what's going to happen? What will be the states that we are going to be, stay in the long run? I know that every state can be broken into two parts, transient and recurrent states. So what do you think that where, in long run the chain is going to stay? In the transient states or in the recurrent states? Okay? So that's our intuition actually. So here's the thing, I'm going to write it there. If I have a Markov chain, first I will try to do what I'll try to find that which states are transient and which states are recurrent. So I'm going to assign probability 0 that the chain is going to stay in the transient state in long run actually. Okay, so I'll throw away all those states which are transient out of my chain actually. Not out of my chain, but out of my computation of probability, because I know that in long run, these are the states of the chain where the chain is not going to stay. Okay, the process is not going to stay. So we will be only interested in what? Those states which are recurrent. And we will try to basically compute that out of all these recurrent states, which states have long run probabilities. Okay, they are going to have certainly long run probabilities, but what are their probabilities in long run actually? That the chain is going to stay in the recurrent states, but which of the recurrent states in the long run? That's what it is essentially.
So transient Q, transient
Transients they are the states.
Return only probability less than 1.
So in other words, you have less and less chances that you're going to return back to the same state. Okay, in the long run. Just look at the definition and have an intuitive picture. All right. So let me write the theorem. Okay. One of the key theorems, and then I will get into the tailoring the problem. Okay. Here's the theorem. Long-term behavior. Suppose we have a Markov chain, like X, we have Markov chain. Okay. On a finite state space, I think. We're talking about finite Markov chains. And S finite state space S that is, the disjoint union of the transient class where the T, the calligraphic T is the collection of all transient class, and and C, so writing a description of it, where this T is the class of all, the set of all transient class, of all transient classes, and C is the set of irreducible a class. C is irreducible. So precise. Irreducible class of recurrent states. Okay. Recurrent states. Then we can find there is a unique stationary distribution okay, given by pi. It's going to be a vector actually containing the probabilities pi I, the probability that you will stay in long run in the state I actually. So you would stay in long run in the state pi equal to pi I. Where how you can compute pi I? So the pi I can be explicitly computed from mu i's, which I'm going to define in a moment. If I is in this irreducible class of the recurrent, states, and it's going to be 0 if I is a transient class. Okay? Where mu I is the expectation of this random variable Tii that we defined. So that Tii was what? Tij was what? The time, okay, that you reach from the state I to the state j for the first time. Okay. So the first passage time from the state I to state j. So the Tii is what? The first passage time to reach from the state I to the state j. Okay. And how can I compute this? How can I compute? What should be the formula for this? Tii actually. So what value Tii is going to take? So you want to compute expectation. So you need to know that what random variable is taking the values. So it can take 1 and 2 and 3 and 4 multiplied by their probability. Okay. So it's going to be a sum
n times.
n times. What is the probability that you're going to reach from state I to state j in n steps? Like f star then. N steps, because f star I j is going to be f I j or f I
n
n actually. So it goes from 1 to this is what it is actually. Okay. We will see that they are, if you know one of a thing, you can, have other of thing. Okay. So usually we go other way around actually. We compute, for example, when you are solving a practical problem, you compute pi I first, and you deduce these expected, return times from the probability distributions actually. Okay. This mu I is also something that is called the mean recurrence time, so the average recurrence time. Average recurrence time. basic definition. If this average return time is finite, okay, then for the state I, then I will call such a state I as positive recurrent. Okay. And if this guy blows up, then you're gonna call it, it's then I is null recurrent. This is just simple definition, another kind of a classifying the state actually. Though this is not a compulsory definition. What does this result in then? So your Markov chain state space in which you can split the chain into the transient and an irreducible class of what do you say? Recurrent classes, then there is always exist a distribution, okay, of the probabilities, and these probabilities, which is this vector pi I, where the pi I can be interpreted as that what is the long-term probability, okay, that you're going to stay in the state I actually, okay, and these probabilities are related with the expected return times, okay, in this manner actually, the proportional. If you have more and more expected return time, these probabilities are going to be lower. It makes sense actually, okay, and if the expected return time is smaller, these probabilities are going to be higher, equal to 0. Let's put it in action to give you an example. If you do your inspection, you will see that 1 and 2 are, make a picture and you learn how to know that whether a given class is recurrent or transient. Okay, so this 1 and 2 are recurrent. Okay. They are recurrent. And 3, 4, 4 is a transient class. Okay, and I'm interested in computing these long run probabilities. So pi equal to what? Pi is equal to, so this pi 1, pi 2. Since these two classes are, transient, 3 and 4, so I already know that these probabilities are 0. I don't need to compute them. Okay. So the only thing that I will be able to compute, I'm interested in computing is this pi 1 and pi 2. Okay. And how can I compute? What is the most obvious thing that you can say about the vector pi actually? So if pi is representing the probabilities that you're gonna stay there forever, in particular state actually, okay, as a distribution of the probabilities that you're gonna stay in a particular state for long run, what should be its impact when you multiply that with the transition matrix actually? So transition matrix is You have a vector and you want to see that how it is going to go in the next step actually.
If
But
it's
if
longer,
these are long run,
should be the same.
should be the same. Okay. So you have a P and you have your abstract pi, you will multiply them. Since these two things are 0,